Polar. Let us illustrate the difference between polar and non-polar molecules with a little experiment. Over here I have a pipette filled with carbon tetrachloride. I'm going to allow a current of carbon tetrachloride to run down, and then I charge this strip electrically by friction. And let's see if this carbon tetrachloride can be attracted by the strip or not. Can you see there's no attraction at all? But if I take this charged rod and I allow some water to run down, I see that we get quite a considerable attraction. So we can see that water is definitely a polar molecule, whereas carbon tetrachloride is non-polar. Both hydrogen chloride gas and ammonia gas are molecular substances, which means they are not composed of ions that can dissociate in water. Aqueous solutions of these molecular substances in water, however, conduct electric current. How can we explain this? To conduct electric current, ions must be present in the solution. This means that hydrogen chloride gas and ammonia gas must ionize when dissolved in water. When hydrogen chloride gas is bubbled into water, a fairly strong hydrogen bond is formed between the delta negative oxygen end of the neighboring water molecule and the delta plus hydrogen end of the hydrogen chloride molecule. The energy released during the formation of this hydrogen bond is partially used to break the strong intramolecular covalent bond between the hydrogen and the chlorine atom in HCl. The delta negative oxygen end of the neighboring water molecule will repel the shared electron pair even closer to the more electronegative chlorine atom, to such an extent that the shared pair is totally or completely transferred to the chlorine atom. The hydrogen ion or proton released will attract the lone pair from the water molecule into its empty s orbital to acquire the stable electron configuration of the corresponding noble gas, helium. And in the process, the very important hydronium ion and a chloride ion are formed, which renders the solution conducting. This is the molecular equation of the reaction, where water reacts with hydrogen chloride gas to form the very important hydronium ion, which renders the solution acidic, and a chloride ion. In this way, hydrochloric acid is formed. This is the so-called fountain experiment, where we filled this flask with hydrogen chloride gas and then inserted a stopper and a glass tube and inverted the flask in a beaker containing some bromothymol blue in water. When I introduced a little water in this flask, a partial vacuum was created because of the very high solubility of hydrogen chloride gas in water. The atmospheric pressure from outside then forced the water up the tube to form this lovely fountain that you see over here. You can see that the bromothymol blue turned yellow because of the acidic solution it formed. We made hydrogen chloride dissolved in water, which we call hydrochloric acid. When we dissolve ammonia gas in water, then the energy released during the formation of the hydrogen bond between the delta negative end of the ammonia molecule and the delta plus H end of the water molecule is partially used to break the strong intramolecular covalent bond between the hydrogen and the oxygen atom in the water molecule. The proton in this case is transferred to the ammonia molecule, and we get the ammonium ion and also a hydroxide ion, and together they render the solution conducting. This is the molecular equation of the reaction, where ammonia reacts with water to produce the ammonium ion and the hydroxide ion, which renders the solution alkaline in this case. The bond formed here, where both the electrons of the shared pair are donated by the same atom, is called a dative bond. It's also a type of covalent bond. It is just the same as any other covalent bond, with the only difference that both electrons are donated by the same atom. Let me show you what happens in this case. This is the ammonia fountain showing the very high solubility of ammonia gas in water. In this beaker at the bottom here, I put some phenolphthalein indicator, and in the flask we put some ammonia gas, and then I introduced a little bit of water. Some of the ammonia dissolved in the water, creating a partial vacuum. And then the atmospheric pressure forced the water up the tube to produce this lovely little fountain you see here. The phenolphthalein turned red, which indicates that we now formed an alkaline solution. The alkali in this case being ammonium hydroxide. This brings brings us to the study of the three phases of matter: the solids, the liquids, and the gases. We begin our discussion with the gaseous phase, reference number 303 in your workbook. In order to understand the behavior of gases, we need to briefly revise the kinetic molecular theory of matter, which states that matter consists of millions of molecules in continuous motion. Now, the kinetic molecular theory of matter successfully explains the macroscopic properties of matter, such as the pressure, the volume, the temperature, the mass, etc., in terms of the microscopic properties of individual molecules, such as their masses, velocities, kinetic energies, etc. Now, gases consist of billions of molecules in rapid, random, rectilinear motion, which means they move along straight lines between collisions. The molecules are far apart in comparison with the molecular diameters. Gases take the shape and the volume of the container in which it is placed. If more than one gas is placed in the same container, they will rapidly diffuse to give us a homogeneous mixture. According to Dalton's law of partial pressures, the total pressure of the gas mixture is equal to the sum of the partial pressures that each gas would exert if that was the only gas present in the container. Now, gases exert pressure due to numerous collisions of the molecules against the walls of the container. Each colliding molecule undergoes a change in momentum of 2 times the mass of the molecule times the velocity of the molecule. And the force per colliding molecule is given by the change in momentum divided by the time. In other words, the change in momentum per unit time, which is 2 times m times v divided by the time of the interaction during the collision. Now, the macroscopic pressure is the combined effect of all the microscopic changes in momentum per second per unit area, because pressure is defined as the force per unit area. From this, we conclude that gas pressure is determined by 2 factors. In the first place, the number of collisions per second per unit area, which is the square meter. And secondly, the intensity of each of the collisions, which depends on the velocity of the molecules. Now, if I evacuate the air from this can by means of this vacuum pump, then the number of collisions per second per unit area from the outside will exceed the number of collisions per second per unit area from the inside. Therefore, the external pressure will exceed the internal pressure. Let's see what happens. Because of the large intermolecular distances, gases are highly compressible. Boyle's law states that the volume of a given enclosed gas is inversely proportional to the pressure exerted on it on condition that the temperature remains constant. Now, what does it mean, inverse proportionality? If 2 quantities are inversely proportional, it means if the one quantity is increased, the other quantity will decrease. Let's look at this example here. If I decrease the volume in this syringe, the pressure will increase. Let's see. Now, if I double the pressure, the volume will be halved. And if I make the pressure tenfold, the volume becomes only 1/10 of the original value. Now, let's see how the kinetic molecular theory can explain Boyle's law. If I consider a given mass of gas enclosed in a cylinder piston arrangement at volume V1 and under a pressure of P1, and then I increase the pressure in such a way that the volume is halved, then, since temperature is defined as being directly proportional to the average kinetic energy of the particles, and since Boyle's law is always performed at constant temperature, it means that the average kinetic energy of the molecules will remain constant, and therefore the average velocity of the molecules will also remain constant at constant temperature. And then, if we halve the volume, it means that the molecules now move in half the space, and because they move at the same velocity, they will collide twice as often. In other words, we'll have double the number of collisions per second per unit area on the bottom of a piston, and therefore the colliding particles can now support double the pressure. The pressure is doubled. If we look at this formula, which represents Boyle's law, we see if the pressure is doubled, the volume is halved, so that we can get the same product P1, B1, which remains constant. This is the graph for Boyle's law. where P1 and V1 are the coordinates of a given point on the graph. We see if the pressure is small, the volume is large. P2 and V2 are the corresponding coordinates of another point on the graph. If the pressure is large, we find the volume is small. How is the pressure of a gas affected by a change in temperature? I got some air in this flask. I'm pouring cold water over it, and the manometer indicates a drop in the pressure of the gas. But if I heat the gas in this flask with this Bunsen burner, we see the manometer indicates an increase in pressure. We know that the temperature of a gas is directly proportional to the average kinetic energy of the particles. An increase in temperature therefore means an increase in average kinetic energy or an increase in the average velocity of the molecules. So the molecules in the flask here will move faster, causing an increase in the pressure reading due to an increase in the number of collisions per second per unit area, but at the same time we also get an increase in the intensity of each collision. The kinetic molecular theory of gases can only explain the behavior of so-called ideal gases accurately and express their behavior in terms of so-called gas laws. Now, real gases deviate very, very slightly from ideal gas behavior at high temperatures, which could be in the order of room temperature, and low pressures, which could be in the order of atmospheric pressure. And so we can apply the gas laws for ideal gases to real gases under these conditions. Now, what is an ideal gas? An ideal gas is an imaginary gas with the following three important properties. In the first place, an ideal gas only occupies volume by virtue of the motion of the particles. The molecules themselves have no volume at all. This means that the volume of the gas would become equal to 0 cubic meters at the so-called absolute temperature if we cool it right down to this temperature. This is the coldest possible temperature that anything can ever reach. Its value is minus 273.15 degrees Celsius or 0 Kelvin. At this temperature, the molecules of the gas stop moving. And this means that the average kinetic energy of the molecules will become 0. And therefore, the temperature must become 0 because we define temperature as being proportional to the average kinetic energy. Now, the second property of ideal gases is that although there are forces of repulsion between the molecules during collisions, there are no forces of attraction between the molecules. This implies that the molecules will move along straight lines between collisions, and that when we cool the gas down, the gas will not liquefy nor solidify, but it will remain a gas right down to the absolute zero of temperature, which is minus 273.15 degrees Celsius or 0 Kelvin. Now, why will real gases liquefy and solidify when we cool them down? It's because in the case of real gases, we do have minute forces of attraction between the particles. We call them van der Waals forces. And thirdly, the collisions between ideal gas molecules are perfectly elastic, which means that the total kinetic energy of the gas mixture will remain constant. The molecules of any enclosed volume of gas can have a variety of velocities and therefore a variety of kinetic energies. Two molecules colliding head-on could, for example, have 0 kinetic energies because they will stop for a split second. Whereas some molecules in the container, only a few of them, will have very high kinetic energies because of simultaneous collisions of a number of molecules from the same side. Experiments show that the kinetic energies of a sample of gas have the following normal distribution value. We call this a normal distribution curve. On the vertical axis, we have the number of molecules per energy interval, and on the horizontal axis, we have the kinetic energy of the molecules. Let me explain the meaning of this number of molecules per energy interval. This is the distribution of the marks for the final matric exams in science, which also follows a normal distribution, as you can see. We divided the percentage marks on the horizontal axis into 10% intervals, right through to 100%. Now, the ordinates of these bars indicate the number of pupils that scored marks within that particular 10% interval, from 10 to 20%. This will be the number of pupils that obtained marks between 20 and 30%. We find that the majority of pupils scored marks around the average value, close to the average value, which is indicated by this distance here. A very important property of this graph is that the total area under the graph is equal to the number of pupils that wrote the exams. Now let's compare this with our kinetic energy distribution curve. We find here that very few molecules will have very low kinetic energies. The ordinates are small over here, and very few molecules will have high kinetic energies. The majority of molecules will have kinetic energies close to the average value, which is EK1 average at the lower temperature T1. Now, a very important property of this graph again is that the total area under the graph is equal to the number of particles in the container, the number of molecules in the container. We know that temperature is directly proportional to average kinetic energy. So if we increase the temperature to a value T2, the average kinetic energy will increase to the new value, and therefore the peak of the graph will move up the scale, and the graph will go flatter as it goes wider. Why? Because it must include the same area under the graph, because the same number of particles are still in the container. Let's look at a certain minimum kinetic energy value, EA. This line shows the EA value. If I now look at the cross-hatched area beyond that line, we see that a large number of molecules will have kinetic energies greater than or equal to the activation energy at the higher temperature T2. And the small area here indicates that a small number of molecules will have kinetic energies greater than or equal to the activation energy, or EA, at the lower temperature T1. Refer to Module 4, reference number 401.4, to see how the characteristics of the kinetic energy distribution curve are used to explain the factors determining the rates of chemical reactions. We are now ready to study the functional relationships between the macroscopic properties of gases. We know that the volume of any gas is very sensitive to changes of pressure and changes of temperature. We first want to investigate the relationship between the pressure and the temperature of a fixed volume of gas. The volume must remain constant. We can either measure the pressure of the gas in this flask directly by reading the pressure on this Borden gauge in kilopascals, or we can connect the flask containing the gas to a manometer, a mercury manometer in this case. You can see the mercury levels over there at present at room temperature, from there to there. And this is a much more sensitive and a much more accurate way of measuring the pressure. Now, if we look at this gas in this flask, we see that the mercury in the open tube is higher than the mercury in the closed tube. To measure the pressure of the gas, in this case, the difference in the mercury levels, H millimeters mercury, is added to the atmospheric pressure PA to get the gas pressure PG. So gas pressure in this case is atmospheric pressure plus the difference in the mercury levels. Now, at the colder temperature here, we find that the mercury in the open tube is lower than in the closed tube. And in this case, the difference of the mercury levels, H millimeters mercury, is subtracted from the atmospheric pressure PA to obtain the gas pressure. So in this case, the gas pressure is equal to the atmospheric pressure minus the difference in levels. We can convert these pressures in millimeters mercury to kilopascals by dividing by 7,5 millimeters of mercury in every kilopascal. If I put the flask in ice water, I want you to see what happens to the levels of the mercury in the manometer. Can you see how the pressure decreases? In this case, we see the mercury is lower in the open tube than the closed end. And this difference in the number of millimeters, as read on this meter stick at the back here, must now be subtracted from the atmospheric pressure, which was measured as 630 millimeters mercury on the barometer. What is our temperature in this case? The gas temperature is 5 degrees Celsius. Let's see what happens if I replace the ice water with hot water. I want you now again to watch the manometer as I put the flask in the hot water. Let's see. Watch the levels of the mercury. Can you see how the pressure increases? In this case, the mercury in the open tube, can you see it's still rising there? I'll just have to wait a minute for it to settle. Right. Can you see the mercury in the open tube is now higher than the level in the closed tube? So this difference in millimeters that we measure over here must in this case be added to 630, which is the barometric reading or the atmospheric pressure today, to get the pressure of the gas in the flask. Let's see what the temperature of the gas is. It is 85 degrees Celsius. Let's look at the graphical representation of the results. In the same way we measured the pressure of the gas at 0 degrees, 20, 40, 60, 80, and 100 degrees Celsius, and then plotted the pressures against the Celsius temperatures. Although we obtain a straight line, the line doesn't pass through the origin of the graph, which means the pressure is not directly proportional to the Celsius temperatures. If we extrapolate the graph and assume that the pressure will decrease linearly, we find the graph cuts the temperature axis here at minus 273.15 degrees Celsius. And this is the coldest possible temperature that anything can ever reach. And therefore we call it the absolute zero of temperature. Why is this the absolute zero? Well, the pressure at this point will be zero, which means the particles are not colliding with the surface of the container any longer, which means they are motionless. And that means that the average kinetic energy of the particles must be zero, and therefore the temperature must be zero, because temperature is defined as being directly proportional to average kinetic energy. Now, what must we do to the pressure axis in order to cause the straight line to pass through the origin? We must move that axis back through 273.15 degrees. And the only way to make this zero here is to add 273.15 to the minus 273.15. In this way, we create a totally new temperature scale called the Kelvin temperature scale, a much better scale, because this temperature scale starts at the absolute zero, which is the coldest possible temperature, which we call 0 Kelvin. This 0 Kelvin corresponds to minus 273.15 degrees Celsius. On this new scale, 0 degrees Celsius corresponds to 273 Kelvin. And 100 degrees Celsius corresponds to 373 Kelvin. So we convert our Celsius readings to Kelvin by using this formula, simply adding 273 to the Celsius readings. And to convert Kelvin to Celsius, we simply subtract 273 from the Kelvin reading. On this new temperature scale, our straight line does pass through the origin, which means that the pressure is directly proportional to the Kelvin temperature, or the absolute temperature, on condition that the volume remains constant. If I change this proportionality to an equation, I have to introduce a constant of proportionality, K. Taking T across, I get P over T is a constant, which means that P1 over T1 equals P2 over T2, where P1 and T1 are the coordinates of one point on the graph, and P2 and T2 are the coordinates of another point satisfying this graph. You know, this apparatus of ours can actually be used as a thermometer to measure temperatures. The conditions, however, to use this as a thermometer, the so-called constant volume gas thermometer, the gas used in the bulb must be ideal. But you know, real gases almost act ideal at high temperatures, around about room temperature, and at low pressures, around about atmospheric pressure. Helium is the most ideal gas we can get, or the closest to ideal behavior, because it consists only of single monoatomic molecules, which are very, very small, the smallest molecules we know. The volume of these molecules is almost zero as required for ideal gases. And the forces of attraction between the molecules are very, very, very feeble, the smallest forces that we know. The second condition to be met is that the volume of the container must remain constant in all measurements. And the third condition is that we must have a fixed temperature for the upper point on the scale, which is accurately reproducible. Now, the lower fixed point on this new scale is 0 Kelvin, and the upper fixed point that we choose is the so-called triple point of water, where water, ice, and water vapor can exist simultaneously in equilibrium. And this temperature is 273.16 Kelvin. Now, If we look at this graph here, we see the constant volume gas thermometer. We can use this formula P1 over T1 is P2 over T2 to find the temperature. If we measure the pressure at a given temperature, a known temperature, we can find the new temperature if we measure the new pressure of the gas. Let us change the subject of the formula. Swapping the temperatures across, T2 cross multiplied, T1 cross multiplied over there, and we take P1 down, we get this formula. If we now take the T1, the first temperature, to be the triple point of water, which is 273.16 Kelvin, then the pressure corresponding to that will be the triple point pressure. And P2 will be the pressure at the unknown temperature. If I look at my PT graph, let us say the pressure at the triple point is 200 kPa, the triple point temperature being 273.16 Kelvin. And let us say we measure a pressure of 600 kPa at the unknown temperature. Then the temperature can either be read straight off the graph, or we can use this formula over here, where we substitute the pressure of the gas at the unknown temperature as 600 kPa, and the triple point pressure 200 kPa, and we find a temperature of 819.5 Kelvin. We can convert this to a Celsius temperature by subtracting 273 to get 546.5 degrees Celsius. We next investigate the relationship between the volume and the pressure of an enclosed gas at constant temperature, and this is called Boyle's law. We use this apparatus to illustrate Boyle's law, where this reservoir was filled with oil. The connecting tube, as well as part of this glass tube, is filled with oil. And you see, above the oil in this reservoir, we have an air cavity. And when we pump air into this air cavity, the gauge indicates the pressure directly in kilopascals. This pressure is transmitted via the oil and then exerted on the dry air, which is captured at the end of the tube here. The volume of the air at the moment is, 8.9 cubic centimeters. And the corresponding pressure reading here on the gauge is approximately 360 kilopascals. By allowing some air to escape from the reservoir here, we can reduce the pressure, as you can see. And what happened to the volume? It increased. We take the new volume and the new pressure readings, and of course we have to wait for the oil to drain down the sides of the tube first, otherwise we will not get a correct reading for the volume. I'll repeat this process, and I want you to look at both the increase of the volume as well as the decrease in pressure simultaneously. We repeat the process over and over. Can you see as the pressure is reduced, every time there's an increase in the volume. And if we do this over and over, we get a number of corresponding pressure and volume readings. Of course, you've got to remember that every time you've got to wait for the oil to drain down the tube before you take your next set of readings. And we can go on and on like that. Over here, we have a table of results obtained by using this apparatus. These are real, actual experimental values, where we have the pressure in kilopascals, the volume, the inverse of the volume, and the product of pressure and volume. When I plot the pressure in kilopascals against the volume in cubic centimeters, I get a hyperbola. But when we plot the pressure in kilopascals against the inverse of the volume, we obtain this beautiful straight line which passes through the origin. What does that prove? It proves that the volume of an enclosed gas is inversely proportional to the pressure exerted on it, on condition, of course, that the temperature remains constant, and that is called Boyle's law. We can represent Boyle's law symbolically as follows. The volume is inversely proportional to pressure. We convert this proportionality to an equation by introducing a constant of proportionality K. Taking pressure across, I get the product of P and V is a constant, which means that P1V1 equals P2V2. You see, the small pressure P1 corresponds to the large volume V1, and those are the coordinates of one point on the graph. And the large pressure P2 corresponds to the small volume V2, which are coordinates of another point on this hyperbola. If we look at our table of results, we find that the product of P and V, expressed in joules, remains constant for all practical purposes. If I therefore go and I plot the product of PV against the pressure in kilopascals. We obtain this straight line parallel to the pressure axis. Why? Because the product of P and V remains constant if the temperature remains constant. In practice, gases are more often subjected to variations of all three the variables, pressure, temperature, and volume simultaneously. Now, we want to derive the functional relationship between these variables, and we call this functional relationship the general gas equation. From Boyle's law, we know that the pressure is inversely proportional to the volume, on condition, of course, that the temperature remains constant, equation 1. And from the ideal gas thermometer experiment, we found that the pressure is directly proportional to the Kelvin temperature, on condition, of course, that the volume remains constant, equation 2. But if I combine these two proportionalities from equations 1 and 2, I obtain this expression where P is directly proportional to the Kelvin temperature, but at the same time inversely proportional to volume. I can change this proportionality to an equation by introducing the constant of proportionality K. And then if I take V across, I find PV is KT, which is the general gas equation or the ideal gas equation. The problem, however, is that this equation is not of much practical use because for every new sample of gas used in a container, the value of K will be different. If we take volume, a larger volume of gas, at a given pressure and at a given temperature, the value of K will be larger and so on. We can solve the problem as follows. If we always use the same volume of gas in the container, then the value of K will always have the same value. If we use 1 mole of any gas in the container, then K has the special symbol R, and we call this the universal gas constant, which has a value of 8,31 joule per mole Kelvin. So for 1 mole of gas, PV is equal to RT, where R takes the place of K. For 2 moles of gas, PV will be 2RT. For 3 moles of gas, PV will be 3RT. So for n moles of gas, the ideal gas equation becomes PV is equal to nRT, which is the most useful formula used in exams. But I want to warn you at this point of time that you can only use this equation if you express each of the quantities in a specific unit and nothing else. If you use this equation, P always stands for gas pressure in pascals and nothing else but pascals. And a pascal is a Newton per square meter. We must remember that 1 kilopascal is 1,000 pascals because kilo means 1,000, or 10 to the power 3 pascals. V is always the volume of the gas in cubic meters and nothing but cubic meters. 1 cubic decimeter is around about 1 liter or 1,000th of a cubic meter. So we've got to divide by 1,000 or multiply by 10 to the power minus 3 to convert cubic decimeters to cubic meters. 1 cubic centimeter is approximately 1 milliliter, and because there are 1,000,000 cubic centimeters in a cubic meter, we now have to divide by 1,000,000 to convert cubic centimeters to cubic meters, or multiply by 10 to the power minus 6. N is the number of moles of gas in the container, and we use this formula where M is the mass of the gas in grams, and capital M is the molar mass or the mass of 1 mole of gas. R is, of course, the universal gas constant with a value of 8,31 joule per mole Kelvin. And T is the temperature in Kelvin, so we have to add 273 to the Celsius reading to express our temperature in Kelvin. Let us calculate the value of R. By using our ideal gas equation, PV is nRT, changing the subject of the formula, we find R is PV over NT. But we know that 1 mole of any gas at STP, which means standard temperature of 0 degrees Celsius or 273 Kelvin, and standard pressure, which is 760 millimeters mercury, or dividing by 7,5, I get kilopascals, 101,33 kilopascals, or roughly 100 kilopascals, or called 1 atmosphere, will always be 22,4 cubic decimeters. Substituting these values in the equation, we find for the standard pressure 101,33 kilopascals, but we have to multiply by 10 to the power 3 for the kilo. And a pascal is a Newton per square meter, times the volume, which is 22,4 cubic decimeters. We have to divide by 1,000 to convert the cubic decimeters to cubic meters, remember. And we used 1 mole of gas. and the standard temperature is 273.15 Kelvin, and this will yield a result of 8.31 joules per mole Kelvin for the universal gas constant R. We can derive the relationship between the pressure, the volume, and the temperature of a gas as follows. We call this the combined gas law. We start off with a general gas equation, PV is KT. Taking temperature across, we get PV over T is a constant, which means that P1 V1 over T1 equals P2 V2 over T2, where P1, V1, and T1 are the pressure, the volume, and the temperature before the change, and P2, V2, and T2 are the pressure, volume, and temperature after the change. If we keep the pressure constant, it means P1 equals P2. What do we get then? We get the formula V1 over T1 is V2 over T2, and this means that the volume of an enclosed gas is always directly proportional to the Kelvin temperature, on condition that the pressure remains constant.